Tonight, we have the great pleasure to welcome NASA scientist Dr. Bos.
After majoring in honors physics at the University of Michigan, Dr. Bos completed his PhD work at the University of Arizona, where he came to join the Mars Atmospheric and Geologic Imaging Team at the Lunar and Planetary Laboratory. In April 2002, he joined NASA to develop the James Webb Space Telescope. He first worked on the OSIRIS-REx mission concept in late 2010.
From 2011, he became the TAG CAMS specialist, which are the touch-and-go camera system, instrument scientist, and continues to serve in that role today. Dr. Bos is also currently the Vision Systems lead for the Da Vinci Plus Venus probe and the Mars Sample Return Capture and Containment Module. He is also currently supporting the Lucy Trojan asteroid mission as a subject matter expert as well.
Dr. Bos is credited as an inventor on 31 United States patents and was awarded the NASA Outstanding Leadership Medal in June 2016 for his work as a NASA civil servant. In May 2016, the International Astronomical Union named Asteroid 120285 Brent Bos in his honor for his contributions to various space exploration missions. He was born and raised in West Michigan and currently lives with his wife and 3 children in Maryland outside of Washington, D.C.
Excuse me. The OSIRIS-REx asteroid sample return mission is Dr. Brent Bos's 5th planetary mission to have successfully left Earth's gravity, but is only his first mission to visit an asteroid. So, Dr. Bos will be speaking to us today about his experiences, and thank you for joining us today. The floor is yours.
All right. Hi. Thanks, Chris. Thanks, Matilda, for the nice introduction. I'm really happy to share with you some of the exciting work we've recently completed at NASA. So hopefully you'll be able to tell how still kind of fresh and new, exciting it is to all of us that we're working on the mission. So let me go ahead and share the charts here. All right, can you folks see the charts?
Yeah.
All right, very good. Well, let's go ahead and get started. I got a lot to cover. So this is what I plan on sharing with you this afternoon. So first I'll give you a brief introduction on OSIRIS-REx and why we initiated this mission in the first place. And then I'll talk about two primary things that are the most interesting from my perspective that were surprises or unexpected and things that we really dealt with from an operations standpoint and were challenges as we went through the mission. And then finally, I'll end with just a quick summary and talk a little bit about what the future plans are for the mission. So OSIRIS-REx is an asteroid sample return mission, and OSIRIS-REx actually is an acronym. It's a rather tortured acronym, however. It stands for Origin, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. So our original lead for the mission, Mike Drake at the University of Arizona, really liked this whole idea of Egyptian mythology, and we really kind of stretched ourselves to stay within that type of nomenclature. So that's what OSIRIS-REx stands for, and you'll see we'll touch on some of those words in that acronym as we go through today's presentation. The mission was selected back in May of 2011, and this was after several rounds of competitive proposals that had gone on several years before. So I think we had lost out on 2 other occasions to get funding from NASA headquarters to fly this mission. But finally, we were selected, I think, on our 3rd attempt in May of 2011. And our original lead for the mission was Mike Drake at the University of Arizona, who was a geochemist and one of my former professors at the University of Arizona. Unfortunately, he passed away about 6 months after we were selected, and which was really a shame because he had worked so long, so many years on finally making this happen. But another researcher from the University of Arizona ended up taking over the lead position for us, and so the University of Arizona is still our lead academic institution on the mission. We launched in September of 2016, and then we're on about a 2-year cruise out to Bennu, a little bit longer than 2 years. We arrived at our target asteroid, which you'll hear me call it Bennu, sometimes RQ-36. Its original name that it gets when it was discovered was 1999 RQ-36. And then we had a contest open to students here in the United States, and they were allowed to come up with names for the asteroid. And Bennu, fitting with the Egyptian mythology, is what we ended up choosing. So we had about a 2-year cruise out to the asteroid. We studied the asteroid for almost 2 years, and then just very recently, back in October, we finally collected our precious sample that we had spent all that time trying to find a good location on the surface to go and collect a sample from. And we believe, as I'll show you, we think we got at least 60 grams of material, which was the minimum amount of material required for mission success. And so that part of the mission, we're mostly done. Now we just have to bring that sample with the spacecraft and the sample return capsule, which is the only part of the spacecraft that returns to Earth. And that will be landing here in the United States in the desert in Utah in September of 2023. So give you a little idea on the sizes of these things we're talking about. So in the upper left here is an artist rendition of, actually this was in our proposal of what our spacecraft looks like. So it's a pretty good size from a planetary spacecraft standpoint. It's about 7 feet per side, so about 2 meters on a side. And we have these large solar panels, which is how we generate our power. When we can't beyond the solar panels, we have lithium-ion batteries, which allow us to operate when we're either in shadow or we can't point the solar rays back at the sun. And we have a number of scientific instruments on board, which cover the X-ray, the visible, and the infrared part of the spectrum. And I'll show you a little bit more about that in just a bit. We also have several laser altimeters or LiDARs on board, which allow us to make topography measurements of the asteroid from orbit. And then one key piece of hardware, which we'll talk a lot about, is the tag SAM. So that's what's shown right here, at least an early rendition of it. And this is what we use to actually touch down on the asteroid surface as well as collect the sample at the end there in the sample head. And then, as I already mentioned, we have the sample return capsule, which you can see kind of peeking out just from the bottom here. And that's the only part of the spacecraft that will actually return to Earth via a parachute and give us our sample in 2023. In the lower right-hand side, this is an artist rendition of Bennu compared to the Great Pyramid of Giza. And although it's obviously much bigger than the Great Pyramid of Giza from an asteroid standpoint, a planetary body standpoint, it's kind of small. It's only about 500 meters in diameter, and the bulk density is also pretty low. So it doesn't generate enough gravity in and of itself to pull itself into a sphere. And it's a very low gravity field, which, as you'll see in some of the animations, makes it difficult to actually even get into orbit about the asteroid. It's almost more like a rendezvous maneuver with another spacecraft. But there is enough gravity there that we were able to orbit the asteroid without burning our thrusters a lot, which was good because that allows us to do other things later in the future. But it's a microgravity environment, so almost like being in a weightless environment. Now I'll show you some pictures of the hardware to give you a feel for the size of these things and kind of what things look like. So this was actually a spectrometer we built at NASA. This was the only piece of flight hardware that NASA itself built. Everything else was built by our partners on the project. And so this was a spectrometer called OSIRIS, which covers the visible to infrared part of the spectrum out to about 5 microns. And so this is how it looks sitting on an optical bench here at Goddard Space Flight Center, which is where I work. And then this is what it looks like sitting on the spacecraft. And this is a picture taken at the Lockheed Martin high bay, which is where we put together and assembled all of the flight components. So everything you see in this picture here are things that made it into space, except for those things that are colored red. So everything that's red has to get removed before launch. And the only thing that's missing on this from the launch configuration are the solar arrays. They were not on the spacecraft at this point. In fact, we don't install those till pretty late in the flow, right before launch down at Cape Canaveral. So this was a picture taken while we were doing some TAG-SAM testing. So you can see TAG-SAM is outstretched here. Again, this is what we use to touch down on the asteroid and gather the sample. And there's the sample head right here, which will actually touch the surface of Bennu. This part right here is not part of the flight hardware. You can see we had to disconnect it here. This is a piece of ground support equipment that we had to use to offset the TAG-SAM, because the TAG-SAM was designed to operate in this microgravity, low gravity field, and it actually wasn't strong enough to operate in the one gravity field of Earth. So what you can't see at the top here is this is actually connected to a large helium balloon that was always kept in the high bay here for just these types of tests where we had to move TAG-SAM around and try to offset its gravity that it produced in the Earth gravity field. And so it always kind of felt like a carnival when you were down there in that Lockheed Martin clean room, because that balloon was always just kind of floating around. Some other things to point out that will be relevant later. So here are two cameras that we used a lot on the mission, NavCam 1 and NavCam 2. We'll show you some images from those. This is one of the LiDAR systems provided by the Canadian Space Agency. It's called OLA. Some other LiDAR systems right here. Already talked about OSIRIS. So again, this is what it looked like once we mounted it on the spacecraft. And then right next to it is another spectrometer that is sensitive further out into the infrared and goes out to about 25 microns. So that spectrometer was built specifically to look at the thermal emission radiation coming off of the asteroid. Right next to it is our largest camera on the spacecraft called Polycam, and it has a large 200 millimeter aperture and allowed us to pick up Bennu from far away when it was just a point source of light like a star, and also offered us some of the images you've seen, like the big mosaic that I show at the end. That was all created by Polycam. It's a very high resolution camera. Right next to it is a camera called MapCam. And then there's two other cameras you can't see, one called SamCam, which is designed to image this head and check out how much sample we acquire. And then there's another camera called STOCAM, which is pointed in this direction at the SRC. And so here's the SRC. This is the actual flight sample return capsule. And this is the only part of the spacecraft that returns to Earth. So it separates kind of down here below where you see this orangish brownish feature. It separates from the spacecraft and comes back down to Earth, and it uses this ablative heat shield to slow itself down, and then deploys a parachute, and hopefully it will touch down gently in the Utah desert. One other instrument is this student experiment called REXUS. So this is our only instrument that's sensitive to X-rays, and it was built by a group of students at MIT and Harvard here in the States. All right, so we get a lot of questions about, okay, why are we going to this particular asteroid? What makes it interesting? And this is a figure from our original proposal, which kind of steps through that logic. So I want to go through that just so you understand why we're going to Bennu, because no one else had ever heard of this asteroid before it was selected for this mission. So back when we were putting the mission together, there were a little over 500,000 asteroids. There's probably almost 1 million now in the catalog. At least last time I looked, I think we were close to that. And so at that time, that's still a lot of asteroids, over 500,000. And we had to use a criteria to start going through that list and figure out where do we want to go with the mission. Well, one of the goals of the mission, obviously, was to go to somewhere interesting and bring back a scientifically important sample. And to be able to do that using the type of spacecraft that we can build and the types of launch vehicles that we have currently available, that meant we had to go to a near-Earth asteroid, which means it's an asteroid that at least spends part of its orbit closer to the sun than what the Earth does. And that allows us to have enough energy and enough fuel to fly out to it, get down to the surface, pick up a sample, and then bring it back to Earth. So that cut us down to about 8,000 near-Earth asteroids to consider. And when we looked at all of the orbital parameters for those bodies, we ended up with a list of about 300 that were optimal for actually bringing back a sample. So not only could we just get there and just get a sample back, we could get those 300 bodies with enough margin that if something went wrong or there was something unexpected, we'd have enough fuel to be able to get the sample back to Earth. So then, around 300, you're starting to get a list that's a little bit more reasonable. The next criteria we used was a size criteria, and there were two reasons for that. One was the orbital dynamicists on the team were telling us that if you go to a body that's too small, it's likely to be spinning too rapidly to land on safely and easily. And it also could have a multi-tilt axis where it's kind of tumbling in space. It'd be really difficult to try to land and retrieve a sample from a body like that. And the geologists on the team were saying if you go to a body that's too small, it's likely that it's going to be really consolidated and there won't be any material, any fine material left that you can actually go and easily excavate and remove and return to Earth. So our criteria was a 200-meter, we had to go to a body that was at least 200 meters in diameter or larger, and that got us down to 27. So now we're talking about a list you can really kind of get your chew on and think about a little bit. And of course, at that point, we were looking to maximize the science we could do. And one of the most interesting things that we thought we could do with this mission was to determine if bodies like these asteroids, these planetesimals left over from the formation of the solar system, if it was bodies like these that could have seeded the early life that could have seeded the early Earth with organics that life could have sprung from. And so of those 27 bodies, there were 5 that were known to be carbonaceous based on the spectra acquired from the ground. And of those 5 bodies, the one that we knew the most was 1999 RQ-36, or Bennu, as we've come to call it. We didn't know a lot about it, but it was the one we knew the most about. And so that's how we ended up going to this particular body. A little more information on Bennu. So the original name itself tells you when it was discovered. It was discovered during the first half of September 1999. Like I said, it's about 1/3 of a mile in diameter, and this is our earliest representation, shown in the upper right here, of what we thought Bennu looked like. This is a model developed from radar observations, actually from Arecibo, which Arecibo's been in the news recently. But these are radar observations from that large radar observatory. And you'll see later, we did a pretty good job. It's like I said, it's not large enough to form itself into a sphere. It kind of has more of a walnut shape to it. But again, it's scientifically interesting for 2 primary reasons. It's a B-type carbonaceous asteroid, so it's likely that it consists of carbon, and we wanted to test the hypothesis that bodies like this could have seeded the early Earth. The other reason this body was interesting, and this is where the security part of that acronym comes into play, was this near-Earth asteroid is one that actually has a non-zero chance of hitting us in the not too distant future. So it could actually strike us in 2169. And one of the goals of the mission is to determine how well we can predict the orbital evolution of small bodies like these, because the orbits of small asteroids like these are not just determined by Newtonian physics. The solar pressure that's always shining on these bodies also alters its orbit and causes it to deviate from what you would just expect from Newtonian mechanics. And one effect in particular is the Yarkovsky effect, which was a goal to try and study and see if we could predict how this body's orbit evolves over time. So here you can see an orbital diagram. This is mostly of the inner solar system. So the green circle here is the Earth, and the blue shows you Bennu. So you can see it's inclined a little bit with respect to Earth's orbit, and it spends a fair amount of its time closer to the Earth or closer to the sun than what the Earth actually does. All right, so that gives you a little bit of background. I'm going to show you now a little video clip that fills in a little bit more details and also kind of bridges the gap from the time we launched to when we were just getting ready to go into orbit about Bennu.
The OSIRIS-REx spacecraft launched in 2016, and it's actually taken us 2 years to get to the asteroid Bennu. And in that time, we had an Earth flyby. So we used an Earth flyby in 2017 to change the plane of our orbit to match Bennu's orbit plane. And it's also provided a great opportunity from a flight dynamics perspective to really calibrate our models and learn how to fly the spacecraft, which will help us in the really challenging part of the mission, which is orbiting in the low gravity environment of the asteroid. Over the past few months, the flight dynamics team has been getting images of the asteroid Bennu, and it started out as just a very small point source in the camera, and it's been getting bigger and bigger and bigger in the field of view. And that's allowed us to perform optical navigation to refine our prediction of the asteroid's orbit and allow us to more precisely navigate and target our approach to the asteroid.
As OSIRIS-REx approaches the asteroid, we've done a series of braking maneuvers called asteroid approach maneuvers to slow down the spacecraft so that we can get into orbit around the asteroid later this year. We're also taking lots of images of Bennu to understand its rotation, look for natural satellites, and potential dust plumes.
This is an extremely exciting time on OSIRIS-REx as we're just poised at arrival at Bennu. And one of the most exciting things to us, and relieving too to the engineers, is how closely the asteroid has resembled what we had predicted. Early on, our science team, prior to launch, had come up with a model of what they thought the asteroid would look like based purely on ground-based radar observations from Arecibo. And from that, they created a reference asteroid that we used as the requirements to design the mission against. But no one could be sure that the asteroid would really look like the scientists had predicted. So it's been a tremendous relief to us to find that the actual Bennu is very similar to what the scientists had predicted. So the science team really nailed it.
Well, right now, as we're approaching asteroid Bennu, we're looking for debris or other objects that are orbiting the asteroid, just in case we need to avoid those. And then once we arrive on December 3rd, we'll perform preliminary survey. And in preliminary survey, we fly over the North Pole, South Pole, and the middle of the asteroid. This helps us to map the gravity of the asteroid and understand how to operate near such a small body. Additionally, this will be the first time that we get close-up pictures of the surface, and we'll know how smooth or rocky the surface that we're going to study is.
As we get closer to asteroid Bennu, we'll begin to map its surface in higher detail. What we'll be able to do is first identify the distribution of rocks and particles that might pose a hazard to the sampling mechanism on the spacecraft. And we'll also get a better sense of what the shape of Bennu is like at smaller scales. Looking at Bennu in more and more detail is going to help us identify all the areas that we shouldn't go to grab a sample from.
Throughout 2019, we'll be doing global characterization of the asteroid, basically making maps of the entire surface. We're interested in its topography. Are there craters? Where are the boulders, the valleys, the mountains of the asteroid? And then we want to understand the distribution of geologic materials. Are we finding different patches of minerals in one location versus another? And why are certain areas that have a composition and others may be different? We're going to be looking, most importantly, for areas where we can collect a sample.
OSIRIS-REx will collect a sample from Bennu using our TAG-SAM, which is the Touch and Go Sample Acquisition Mechanism. What that is an arm connected to this sampler head that you see here. This is similar in size to an air filter from a car. How this mechanism works is there's compressed gas that is released that will stir up the regolith from Bennu, store it into this canister, which we will then put inside of our sample release capsule and bring back to Earth. We will collect the sample of Bennu in 2020 and return it to Earth in 2023.
Once we're in the vicinity of our home world, about 4.5 hours before impacting the top of the atmosphere, the spacecraft spins up and releases that sample return capsule. The spacecraft fires its engines to perform a deflection burn, going off into orbit around the sun, and the return capsule enters the Earth's atmosphere, targeting a landing in the Utah desert. I'll be there on site when we open that capsule up and we see those samples for the first time. And science begins at that point on the next phase of the mission, the sample analysis period.
All right, so that kind of fills in the detail, a little more detail about some other goals of the mission and how we were going to carry it out. And so going back in time to late December 2018, we were had just approached Bennu and we're getting ready to go into orbit about it. And then here in the United States, the federal government shut down because the Congress and the president at the time couldn't agree on a budget. And so that was a big surprise to the project, of course, and we all had to deal with that. And fortunately, some of us that were working operations were given special permission to still work the mission. And so we ended up being able to go in orbit around Bennu on New Year's Eve in 2018. And as the video was talked about a little bit, what we had to do because of the low gravity environment and the difficulty with making sure you're always in orbit about this low gravity body was we were constantly taking pictures several times a day, every day while this was going on. And on January 6th, we noticed in two of the images that came down, in two long exposure images, and these are the actual ones shown here. So you can see this is Bennu overexposed. It's kind of hard to see, but in the background you can actually see stars, and that's how we would determine where we were with respect to the asteroid and if our attitude was correct, and was matching our expectations for being in orbit around Bennu. So we were taking these kind of images all the time, but these two images on that day showed something new. And so that's what the little insets here are meant to show you. You can see there's these little just dots of light, which look like stars, but from frame to frame, it looked like they were moving, and it looked like you could kind of correlate the motion, that it looked like one little point of light here may correspond to one in the other image. But we weren't sure. These were unresolved, just little points of light. And we had seen features kind of like this in single frames when we were doing some other imaging right before we had entered orbit. And these were caused by radiation events. And so we weren't really sure if this was real. It was potentially very exciting for us because asteroids are generally believed to be dead, right? It's comets that are active when they come into the inner solar system and get heated up and start to develop an atmosphere and spew out dust and ions and such. But there's only just a handful of asteroids that are known to do that type of thing. And so seeing this on Bennu was potentially very exciting and interesting from a scientific standpoint. But it was a little bit tenuous in terms of the evidence for this happening. And so we developed a whole fishbone diagram of what could cause this in the images. Could it be spacecraft related? Is it a radiation event? Or is it real? And certainly kind of the leading candidates were either it's real or it's just radiation events that happen to take place just right after each other, which is unlikely but not completely impossible. And of course, your eye can always kind of correlate, particularly things that don't have any features to them. It's kind of easy to correlate things frame to frame. So there's a big discussion, and those of us that were able to work the mission, this was kind of our priority then once we got these images down and tried to figure out what was going on. So a big investigation was started into the possible cause. At the same time, we came up with a whole new imaging scheme, not only to figure out where we were in orbit with respect to Bennu, but also a scheme that would try and see this activity with higher temporal resolution. So we're trying to take a lot more images and also spread out a little bit more around the body to see if we could see anything. And so that was a whole kind of fire drill as well. We uploaded commands to the spacecraft and were able to start that unexpected imaging campaign on January 11. And at the same time, we started to realize, boy, if this is really happening, we don't have the greatest tools right now to analyze this. We're doing everything by hand at that point with very little amount of automation. And so at the same time, we started to develop some tools to help us understand if it was real, what was really happening. Fortunately, it didn't take that long. And on January 19, Bennu cooperated with us and kind of showed us this behavior again. And this time we saw it in more than just 2 frames. I'm showing 4 here, but we had multiple frames that showed, again, these little unresolved points of light. But once you had a higher temporal sampling, you could show that, yeah, in fact, these are unresolved, but you can see frame to frame, they're following a predictable path. And so at that point, we could sort of stop the investigation into all these other potential causes, and we realized this is a real event happening on Bennu, and how interesting from a scientific perspective. At the same time, our tools were just starting to get better, and we were getting ready to really kind of dig into what was happening and really start to understand and develop statistics of what we saw occurring around Bennu. So I'm going to show you some early results first. So the next thing I'm going to show you is an animation of a tool that we developed to look at images like this. And what it does is it removes from the image Bennu, and it takes out any of the stars, known catalog stars that are in the background, as well as any other solar system objects. And so the only little points that you'll see that remain are things we don't know what they are. And you'll see probably a lot of them are just detector noise or other noise sources. But every now and then you'll actually be able to see an ejection event. You'll also be able to see like little trails of orbits of particles. So let me show you that. So fortunately, this type of tool alleviated all the manual work we had to do to identify potential particles and also try and track them. So this was a nice thing that removed some of the workload from the team. So there you see the big event that was on January 19. You'll see some other ones. And you can see now there's some nice trails there. The ones that curve are obviously real particles. And you can see some of them are, there's a nice one on the left. You can see some of these go up and they come right back down. Other ones look like they have real orbits, and other ones are kind of escaping. So this tool allowed us to automatically go in and identify potential particles, and it was a great addition to what we could bring to the problem. We also started to be able to do a better job of just processing the individual frames, so you could get an idea just visually what was happening. So this is the event from January 6th. So it shows Bennu, and then also brings out most of the brighter particles that were being ejected. You can see some of the, go back here, see some of the streaks here from the particles. So that was the big event. That's the first thing that caught our attention, of course. And this was the January 19 event. Again, you can see particles that are ejected kind of off the limb here of the body. Here's a streak, one of the faster moving particles. So with these better tools, what we were able to do, particularly once we had a lot of observations of these particles, you could start to try and fit orbits to these. And that was probably the most interesting thing, because that would allow us to develop statistics. It was also interesting from just understanding the gravity of Bennu. So what I'm going to show you next is an animation that kind of shows the end product of that orbital analysis, and it shows the particles that we were able to fit orbits to for a number of different events. First one is the January 19 event. So in blue, you can see that's where OSIRIS-REx orbit is, and then the yellow are all these particle orbits. And you can see some of them actually crossed our spacecraft's orbital location. Here's one from February 11. Another one from August 28. And I think the next one has a nice view of kind of the event happening right at the top. Yeah, September 14. So once we had studied this for a while and got these tools to work, we were ready to kind of share this with the rest of the community. So we had embargoed this information for quite a while we were just trying to understand and pull everything together. But we finally published the results in Science back about a year ago in December of 2019. I just pulled out some of the more interesting figures, at least from my perspective, from our paper. This one here, I think, tells kind of the best story overall. So it's just a plot of the number of particles that we detected versus calendar day. So it's number of particles per day. And the purple lines show you those events that we consider large events. So, a few hundred particles maybe. The orange shows you smaller events, a little more than a dozen particles detected. And then the aqua color shows that we just detected particles in orbit. It wasn't necessarily an ejection event, but when we took pictures, we saw, oh, there's stuff floating around Bennu. The figure up in the upper right here shows you where we think, at least for the first 3 events that we documented in the paper, where we think those ejection events were located on the surface. So this one on the left here is for January 6, and then January 19, and the final one is February 11. And we use different approaches to try to do that. The ones that are marked in orange kind of gives you an uncertainty envelope. If you just look at the first few observations of a particle and then backtrack in time to where it would have had to come from on the surface. For these 2 later ones, these little yellow circles, that shows you if you include all the orbital data that you have for an ejection event and then backtrack it. And this shows you, we think we have a better idea using that approach as to where the actual location for the ejection event was on Bennu's surface. Unfortunately, we don't have pre and post images of the surface. So there's a lot of conjecture as to what is causing this behavior. And in the paper, I think we had 8 or 9 different things that or hypotheses that we were laying out. But there were really 3 kind of major ones that most people thought could be causing this. And that's sort of changed over time. When we wrote the paper, we thought the most likely thing was that this was caused by thermal fracturing. And because these were all happening kind of in late afternoon, kind of local 2:30, 3:30-ish local time on the asteroid. So what we thought was happening was, it's very cold on the dark side, and then as the body starts to rotate and goes into the sun, the rocks heat up and you have thermal stresses that cause cracks in the rocks. And it doesn't, because it's a low gravity environment, it doesn't take a lot of energy to launch something up into space. So at the time we wrote the paper, that was sort of the leading hypothesis. As time went on, and we observed more of these ejection events, we saw they weren't necessarily as well correlated with that late afternoon occurrence. And so kind of the leading thought now, which was at the time more like our second leading cause, was that this is probably just caused by the normal micrometeoroid flux. Just like we see on Earth, we're seeing shooting stars and some stuff makes it to the ground. Bennu is kind of living in the same type of environment, and the activity is also fairly well correlated. The amount of material and the amount of events are fairly consistent with the particle flux just from the junk that's always flying towards us. And so right now, that's probably more the leading hypothesis. The other one we thought about at the time, that was a leading one at the time of the paper publication, was that it could be caused by a volatile release. So you have these trapped gases inside the rocks. And again, because of that thermal cycling in the afternoon, that heats up and then that material escapes a little bit and all of a sudden causes little explosions and stuff gets sent into space. Again, doesn't take a lot of energy because it's such a low gravity environment. And of course, it could be any combination of those things as well. So it may not be just one mechanism that's making this happen. But unfortunately, we don't have, like I said, we don't have pre and post images. So that sort of lends itself to conjecture and to just a little bit more theoretical approach to try to figure out what was happening. But over time, we developed enough understanding of what was happening. We found that, like was shown in that animation, a lot of particles go up and they kind of comes right back down. We actually did have some instances where you could see a particle came down and it looked like it generated some more particles after it did that. A lot of particles also just have enough energy to escape Bennu's gravity, so they go off on hyperbolic orbits and you never see them come back. But there are a fair number, I think about a quarter to a third of them, that actually go into semi-stable orbits. And that lasts about a week or so, maybe 2 weeks at the longest. And so what that told us was that even though we weren't seeing ejection events all the time, they must be fairly regular, even more so than what we were observing, because anytime we looked around Bennu, there were always particles around there. So these mechanisms, whatever is causing this, is happening enough that the population is always being replenished so that we always see particles anytime we look with the right type of observing campaign. The particles themselves are not that large. They range in size from about 1 to 10 centimeters, so about the size of a softball. And they don't travel that fast either. About 7 miles per hour is the fastest we had observed. And that was a big interest, of course, to the spacecraft team, because when we first saw this happening and thought maybe these were real ejection events, the thought was, are we safe enough to stay in orbit, or are we going to damage the spacecraft? At the time, the team decided it was worth staying in orbit because it was kind of a big risk to leave orbit at that point, just because of everything going on operationally. And we weren't really sure if it was real and what the real danger was. But once we had observed enough particles and enough events, we were able to run the statistics. And the guys that on the spacecraft team that actually do the analysis to figure out whether or not it's safe to launch through all the crud that's surrounds the Earth when we launch, they use the same type of analyses and the same type of risk assessment to determine whether or not we should stay in orbit about Bennu, and found out that actually was quite a bit less risky to stay in orbit about Bennu than what it was to launch through all the stuff that's circling Earth right now. So that was, in my mind, was kind of the biggest surprise from our science operations phase. And of course, it kind of played out over the very early part of being in orbit about Bennu. So now I'm going to show you another video clip that kind of takes you from that time frame up until about late September, early October. So just this past fall when we were getting ready to do the target or the sample acquisition.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and We saw very few areas that had this sandy surface that we were expecting and what we had designed to.
We have never done this before. We're actually going to collect a sample and bring it back down to Earth for further examination by scientists.
In order to achieve that objective, the OSIRIS-REx spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller. We realized that there were no sites on Bennu that even came close to meeting this criteria. Everywhere we looked was too small and covered with boulders. So we actually had to fly a number of additional close passes over the asteroid and rethink our entire plan for grabbing the sample. After the additional observations of Bennu, we had to down select to 4 sites and then go back and survey those sites even further to select the final primary sample site.
My first impression of Nightingale is that's the last place I wanted to go. But as we started looking at other sites, we saw that 1, this is probably one of the most sampleable sites, and 2, we were overperforming in our navigation capability and our ability to contact. Natural feature tracking works a lot like the human mind in that we pick up landmarks along the way. As we descend, we look at features on the ground. We program the computer to recognize certain features. It takes a picture, says this feature is not where I expected it to be, it's a little bit off to the side, updates its position based on where it's pointed and where that feature shows up in the camera position.
The tag event is our touch and go event, which is where we'll actually be retrieving the sample from asteroid Bennu. We start with a series of maneuvers, one of them being the checkpoint burn, which is where we'll actually check our position velocity in relation to the sample sites.
And then the match point burn, about 10 minutes later, we'll zero out our horizontal velocity relative to the surface. And then about 10 minutes after that, we make contact with the tag SAM, fire the gas bottle, and then back away.
And we hope to get at least 60 grams of sample, and then we'll be able to store that and bring it back down to Earth.
But there are several things that could go wrong, and we also have to be prepared that we won't be successful on our first try at Nightingale.
We don't only get one shot at tag. We actually have 3 nitrogen bottles on board the spacecraft, so we can potentially do 3 tag attempts if needed. We go through several what-if scenarios, and this is how we actually prepare for a lot of our contingencies.
So we've had to look all around the surface and identify the rocks and boulders that if the spacecraft were to tip over up to 25 degrees, it could come into contact and be damaged.
We had to develop a hazard map, which we program into the computer and says, if you're getting too close to those hazards, we'll do a wave off, we'll back away from the asteroid, and we'll come back and do this another day.
Everything might work perfectly. We come down, we touch the surface just where we want to, we fire the gas bottle, but the area we contact is covered in large rocks. Those rocks would prevent any fine-grained material from being stirred up and captured in the tag SAM head. Another similar scenario is if the tag SAM were to touch on the edge of a boulder and become tipped up. In that case, when the gas bottle fires, much of that gas escapes out the side, not churning up the material that we want to capture. The day of tag is going to be really exciting, but the excitement for our team doesn't end there.
We have to verify that we have a proper sample.
First, we're going to image the tag SAM head by sticking it in front of one of the cameras. Then we're going to do a maneuver called the sample mass measurement, in which we stick out the arm and we spin the spacecraft in order for us to decide if we've collected enough mass to be able to stow the sample and return home, or if we have to try again.
This is the culmination of a lot of work. It's probably one of the most exciting missions that I've worked on.
It is really exciting to know that we're finally going to be able to touch the surface of the asteroid and collect the sample to return back to Earth.
All right, so that kind of shows you where our heads were at and what we had to go through up until the point of tag. So our first sample acquisition attempt, or tag, took place on October 20, so it's still kind of recent memory. It's still even kind of exciting to think about. This shows you where Bennu was when we attempted this. So here's an orbital diagram. Earth is way over here, and Bennu's over here. So we were over 2.2 astronomical units away from Bennu at that point. And actually, we were farther away from Bennu than almost anything else in the inner solar system at that point, if you look at where Mercury and Venus and Mars were. And this was our sampling site. It was called Nightingale. And we were trying to fly into this area where we thought there were carbonates, but was also safe. So that was the key thing. Safety was the prime factor, and then the secondary consideration was, okay, well, will it be an interesting sample? And so I'm going to show you next a short video clip that shows you from the SAMCAM perspective how it looked as we went down. You'll see the head, and you'll see us punch through the surface. So there we are descending to the surface about 4 centimeters per second, and then we straighten up the head right before we make contact, and then we backed away. You can see it looks like we made a hole and we made a big mess. I'm going to show you another animation. It's a longer one, which is from the perspective of NavCam 2. And these images are the actual images that the spacecraft itself used to figure out if it was on the right trajectory and to decide on board automatically, because we're too far away from Bennu to do this interactively. So the spacecraft was deciding as it flew down, okay, am I seeing what what I should be seeing if I'm on the right trajectory? So that's what I'll show you next. It shows you from the point of orbit departure all the way down to the surface, down to surface contact, and then about 1.5 minutes of the back away. So there we are leaving orbit. And now you can see the landing site just up in there in the upper, just to the right. Now it's out of the field of view, but you'll see the TAGSAM shadow come in. It'll give you a good indication of where we touched down. So there's the TAGSAM shadow, and then we make contact. And now you can see it's just kind of chaos. It's, what is going on here? It's very, this was very interesting when it first came down. I'll show you a little bit more of this in a little bit. So you can still see some of the surface there, but there's also a lot of suspended material, stuff just flying around. So of course, we didn't see this right away. We didn't have the bandwidth to get these images down all that quickly. I think that parts of this movie actually didn't come down even till early the next day. But we did get telemetry almost right away from some of the simpler sensors on the spacecraft. And the one that was most interesting was on the TAGSAM forearm. So on the TAGSAM, again, this is the piece where actually the only part of the spacecraft that touches on the asteroid. So it's spring loaded, kind of like a pogo stick. And we had a sensor on board that when the spring was depressed to a certain level, that sensor would trip. And that was equivalent to a pushback force of 65 newtons. And so that was what our primary decision point, or the decision maker, would be to decide whether or not to blow the nitrogen bottle to start the sample collection, and then a few seconds later to start the back-away burn to move from the spacecraft. But what we saw in the telemetry within about 20 minutes of all this happening was that sensor actually never got tripped. And so what ended up triggering the sample acquisition procedure and the back-away maneuver was actually a clock we had running on board the spacecraft, and the spacecraft, it was looking at its altitude as it was going down, and when it took its last picture based on its velocity, it said, okay, I should be touched down in about 5 more seconds. And when it didn't sense this trigger, it waited a few more seconds and said, okay, we must have touched down or something went wrong, and triggered the nitrogen gas release and triggered the back-away burn as well. So that's what actually ended up triggering the sample acquisition, which was great. I mean, it was a backup, and we had thought about the types of scenarios of that this surface could be so unconsolidated, it could be just like a fluff, that you had the potential of flying into it and burying the arm and potentially even burying the spacecraft. And it's good we had that, because that's sort of what could have happened if we hadn't had that in. And if you look at what 65 newtons corresponds to here on Earth, that's only about 15 pounds. And so that's about the size of an adult bowling ball. And if you think about the strength of materials here on Earth in terms of surface material, the surface we flew into had about the same strength, about the same consistency as freshly fallen snow. So if you think about taking a bowling ball or something that weighs 15 pounds and just kind of dropping it into freshly fallen snow, that's the same type of dynamics we think we were encountering on the surface. It's a perfect analogy, actually, if you take 15 pounds and you distribute it over like a pizza pan, which is 12 inches or about a foot in diameter, because that's how large the TAGSAM head was. So it was very interesting to really start to understand that what we flew into offered almost no resistance. And of course, then in addition to the telemetry, like I said, over the course of the next 12 hours or so, we started to get the images down. This is a still shot from that movie I showed you, and it shows where we actually touched down with the head. So that's about a foot in diameter circle right there. And then this shows you kind of the last image from the Navcam 2 perspective as to where we touched down. So it helps you kind of orientate yourself a little bit. And at this point, while these images were coming down, everybody was kind of digging into this, trying to figure out what was going on, particularly because that backaway event looked so chaotic and so much more dynamical than what we had originally anticipated. So I'll show you a little bit of the early work, or kind of the early things we did to try to understand even what was happening. This is another single frame from that animation I showed you from Navcam 2. And we started to use these to, okay, we can kind of figure out what's going on. There were actually parts of the surface, so they're kind of called out here, surface 1, surface 2, and surface 3. There were parts of the surface that were completely unperturbed, or mostly stable. So that helped us orientate ourselves as to where we were even looking. And then, of course, we saw a lot of material was flying around. There was a very early on kind of argument as to whether this was actually what you see as kind of the smooth, bright area, if that was just a new berm that we had created by, punching into the surface and then also executing our burn, which freed up some material as well. But we found out this was actually kind of a plume that was moving away from the asteroid, separate from the surface. And it was moving at about a third of the velocity of the spacecraft itself. So it was sort of following us as we backed away. So what I'll show you now is just interesting stuff that we're still trying to kind of understand, but really grabbed our attention early on. So I'm going to show you a zoomed in version of the video that shows you this rock kind of falling, just tumbling around in microgravity. And then there's this rock that we called the impactor that ended up tumbling around as well, but didn't quite have the altitude to make it off the surface and ends up hitting this larger rock here. And then the next video I'll show zooms in on this area right here around this very large bright rock, which actually seemed to be stronger than anything else in the whole image, because it gets hit by things and sort of gets jostled around, but you don't see it break apart. And it's again, to give you a size, an idea of the scale, it's about 5 inches or 130 millimeters in diameter. So first I'll show you the video on the lower left here, and then I'll show you the video close up of some interesting things happening inside this plume as it's moving away from the asteroid surface. So here's the bright rock shown on the left-hand side here. And then here's this rock, which is also tumbling around, but isn't as high as that rock on the left. And it ends up striking this other rock and then breaks apart. Looks like it kind of rolls back down to the surface or just disappears. And then this is the video in reverse, just to help your eye follow what's going on. And you can see there's a lot of other things flying around and hitting each other as well. So we think a lot of the finds that we were seeing were these larger rocks hitting each other and grinding each other up and producing this fine sort of backscatter. All right, so I'm going to show you the video of that bright rock again. It's about 5 inches, about the size of a men's shot put. So you'll see it kind of come up from the plume. And then two other rocks kind of bunch up against it. And the rock on the outside actually gets hit by another rock and gets broken apart and sort of falls back into small pieces. And this will play in reverse again to help you kind of follow it. So this was all very interesting and kind of unexpected. As you can see in the animations, that's not quite what we expected. We were hoping or kind of expecting for kind of a thin layer of fine material, and you end up hitting something hard and you get that material. But you can see this, the surface offered almost no resistance, and we kicked up a lot more material than what at least a lot of us were thinking might actually happen. And so there was a lot of effort put into understanding these images as they were coming down. It was all very exciting for the first few days there. But then just 2 days later, we had to go, like we showed in that video, we started to take pictures of the sampling head to start to get an idea on how successful the sample acquisition attempt had been. And so these are images taken by SAMCAM on October 22. And you can see it looks like there's a lot of material stuffed in the rim, which was the plan. Of course, it doesn't look like a lot of light is coming through the mesh. But as is obvious, I think, to anybody, it looks like we're leaking material. And so it was sort of a good news, bad news response at that point once we saw these images. In fact, if you look in here, you can see kind of where these wrinkles are. That shows that the flaps that were designed to close after the sample acquisition attempt had been finished, some of the flaps were kind of stuck open. So it looked like we had collected so much material that the flaps themselves couldn't even close. So this, all of a sudden, all of our attention went from understanding what we had done during tag and what we had kicked up to trying to understand what was happening here. And so that was on the Thursday where we got the images down. By the next day, we had several different groups who had gone through and painstakingly looked at every image and tried to estimate how much material was in the head and how much material was leaking every time we moved the arm or the spacecraft. And by that Friday afternoon, we were pretty sure we kind of had a problem. We thought we had probably acquired even as much as 600 or 700 grams of material. But it looked like every time we moved either the spacecraft or the arm around that we were losing about 10 grams. So at that point, we decided we needed a new plan. We made a presentation to NASA headquarters on Saturday afternoon, showed them what was going on and said, we're going to skip all the stuff we talked about previously and was shown in the video, all the things we were going to do after tag. And we think we should throw everything out except for those maneuvers and those operations that get us to a point where we can safely put the sample head into the sample return capsule. And so fortunately, headquarters agreed on that Saturday afternoon. And at that point, the team began an almost round-the-clock continuous operations. Not totally 24 hours, but it was close. So by Tuesday, we were ready to open the sample return capsule. So that was October 27. Later that day and early into the morning of Wednesday, October 28, we actually were able to get the sample head stowed into the SRC. And then later on Wednesday, we pulled back on the head to make sure it was securely in the sample return capsule. And then later that same day, we cut the tubes that were connecting the nitrogen gas lines to the nitrogen bottles to the head. We also fired a frangible bolt, which separated mechanically kind of the forearm of the tag SAM from the rest of the sample head. And then late on Wednesday, right before midnight, we closed the SRC. And that whole process took about 28 hours from beginning to end, from opening the sample return capsule to doing all those steps. And this process, unlike the sample acquisition, which was all done automatically on board, this all was person in the loop. So we had to do little steps, send stuff back to the ground, look at the images, make sure things were proceeding properly, and then we would issue the next command. So that's why it was so labor intensive. So I'm going to show you the short video that takes that 28 hours into about 46 seconds or so. So there's the SRC as how it looks from the STOCAM's perspective. So we open the cover, and then you'll see the sample head. So there's the sample head. It gets pushed down into these latches. There's actually 3 of them. One you can't see on the other side. And then the next frames will show you we tried to pull on it to pull it back out to prove to ourselves it was safely secured. And then once we knew that was safe, we cut the nitrogen tube, blew the frangible bolt, moved the arm out of the way, and then closed the SRC cover. You can still see, if you looked in the background there, you could still see some particles floating around. So OSIRIS-REx, we believe that we acquired at least 60 grams of material. So we did an analysis looking at the timeline and our motions. We think we still probably have several hundred grams of material. We don't know for sure yet because we had to skip all those sort of confirmation steps that we'd originally planned to do. But the spacecraft itself is healthy and well, and it's ready for a return cruise to Earth. And now that that sort of emergency is out of the way of stowing the sample, the team is back to trying to analyze really what we did to the Bennu surface and understand that imagery. And in fact, there's been so much interest in this where very recently, this is a new decision by the project and concurred with by NASA headquarters. Because this is so interesting, we have decided to break one of the mission rules, which was once you get the sample, you don't go back to Bennu, you don't do anything to jeopardize it, you just try to get it back to Earth. Well, we've decided that we were going to do one more low flyby over the sampling site to see what's left and what it looks like now, so we can at least get a pre and a post comparison to help better confirm and constrain our models and our hypotheses as to how strong the surface was and what we actually did to it. So that's very exciting. We're going to do that now, April 6th. So the team was sort of a little bit in semi-retirement mode, and now we're starting to get Jen back up to get ready to do this flyby on April 6th. We're going to leave Bennu. Right now, it's nominally planned for later in the spring, so May 10 is the nominal date. We also have a backup date of May 24, just in case something goes wrong. But no matter when we leave, we'll be arriving here in the States in the Utah desert at the Dugway Proving Grounds on September 24 of 2023. And it's that point, a lot of our geochemists on the team like to remind us that that's when the real science actually starts. So that material will be brought to the Johnson Space Center, and there's a facility there where all of NASA's planetary samples are stored, the Apollo moon rocks, things from other sample return missions, even the Japanese asteroid missions that have returned some samples. There'll be a small sample of them there as well. And we've actually paid, these are actual pictures of what it looks like now, but we're currently upgrading that facility, which is shown on the right, the architect's plans for upgrading that facility. And at that point, once we get those samples there, our team will be, our geochemists on the team will be looking at that, but anyone around the world will be able to make a proposal to NASA to get some of the samples and analyze them for themselves. And it's likely that's where even the more exciting science is going to come from. So that's all I had to show you today. I don't know if we got time for questions. Went a little longer than what I'd expected.
No, that's fine. Thank you so much for this talk. That was really interesting. So we have a question from the audience. Edouard Demers asks, how did the experiment from MIT/Harvard go? What was it looking at, and did it work according to plans?
Yeah, the Rexus experiment had a number of issues, and so we didn't learn a lot about Bennu from it. I think they published one paper that was an observation of a new X-ray source that someone else in the X-ray community had discovered, and the team went back and looked through their data. They had seen a bright X-ray source and wasn't sure what it was, and then people started to publish that they had seen this new X-ray source. So I think they published on that. There were a lot of issues. There were some thermal issues with it. It was a student experiment, and in fact, there were some problems with it up until the last minute even. And so we had a team that went from NASA to go up there to Massachusetts to help that team to get it going. So it did work to some level, but it really wasn't. And because it was a student experiment, the project wasn't necessarily relying on any results from it in order to do the key things in the mission. So I'm hoping they'll still be able to do some more advanced data analysis, and they'll give us some X-ray images, or at least a little bit of more information about Bennu. But at this point, they still haven't really published anything about Bennu anyway.
Fantastic, thank you, and thank you as well for your really great talk. It was just amazing to see some of those pictures. That some of them have been circulated around, but understanding really the science behind it is really great. I wanted to talk a little bit about those particle ejections. In terms of the mechanisms behind them, what do you think is necessary to be able to confidently identify which mechanism might be the main one? What experiment would you like to do?
Yeah, so that I kind of skipped over it since we were taking up a lot of time. So the other thing that we might do with OSIRIS-REx, because once we deliver the sample back to Earth, we've done a really good job with managing our fuel, and because the spacecraft is in and the instruments are in good condition. Right now, we're developing a proposal to go to another near-Earth asteroid called Apophis, which people might be aware of if you kind of follow. Every now and then there's hysteria about, a new body that might hit us. Well, Apophis is going to fly by us very closely in 2029. And one of the key science experiments we're proposing as part of our mission would be to do a similar particle ejection survey and see if this body, which is a different type of asteroid, if it's also ejecting particles at about the same rate, that would lend itself to the theory that, oh, it's mostly caused by just this meteorite flux. So going to a completely different body could really help us understand that. If we don't see anything, then yeah, there's something unique about what Bennu is made out of and what's happening on its surface compared to this other body. So I think that's a really strong argument for going to Apophis or any other, asteroid. If any other asteroid missions that follow can start to look for this kind of thing. So I am involved, like I think in the intro, someone talked about the Lucy Trojan asteroid mission. We may look for that type of behavior as well. But of course, those are out near Jupiter's orbit. But if you saw ejection events there at about the same, regularity, then that would lend itself to not being just part of the normal meteorite flux that we're subject to. So, yeah, it's always new discoveries like this also lend itself to new investigation. So it'll be interesting to see. I mean, everybody is just, again, I didn't emphasize it as much, but the project's main goal was just to find the most interesting place on the surface to to grab a sample from. And that's what that 2 years was really mostly dedicated to. If the particle ejection thing had been a key science goal, we would have done a lot more flybys close in and tried to do a lot more global mapping, to try to show before and after. But we really only have kind of the one big global map. So if you're really trying to nail down that particle ejection thing, you would want to do a bunch of global imaging, on a regular basis, maybe like once every month or every couple of months. And then you could really do a pre and post and really get a good idea. Does it look like, something struck it? Is it a whole crater around there? Or can you not even see? Is it just so small that it's just little cracks where these particles had enough energy to just, start radiating away from the surface? So, those of us that were heavily involved in it were really interested in trying to push for that kind of thing. But we were happy, just once we proved what it was, we did add a lot of imaging that wasn't planned to just look for that kind of activity. So we were a lot busier imaging than what we had planned. So we did have some leeway there to try and investigate that further.
So we have a follow-up question, another question from the audience. What will happen with the spacecraft for the end of life? Will it burn up in Earth's atmosphere, or just will we just forget it in space?
So yeah, there are two possibilities. So once the spacecraft flies back to Earth, the sample return capsule will separate. That part will go back to Earth. Right now, the nominal plan, the plan that we had proposed to headquarters, is that we'll do a final burn, which will put it in a sun orbit, designed to minimize the likelihood that it will impact any of the interesting bodies in the solar system so that we don't contaminate them in the future. I forget what the lifetime for that is supposed to be, because obviously at some point we're going to hit something, but it's something like over 100 years or several hundred years or something like that. So it'll likely be left in space. Or if we get this additional funding to fly out to Apophis, then that'll be, we may even rename it. It may not be called OSIRIS-REx anymore. We may have another name for the mission. But if we get selected to do the Apophis rendezvous and go into orbit about it, then we'll be doing that until 2029. And depending on how we manage fuel, we may at that point decide to just stay in orbit around Apophis and study it until we run out of fuel, or there might be some other follow-on mission. But we're really hoping we get to continue flying and go look at Apophis.
Thank you. And I think it's if anything, it's a testament to how well the mission was built and run to say that we can possibly even do a second mission to other asteroids as well. So just in the interest of time, obviously we can keep talking if we're lucky to have you, but we do like to sort of end with an address directly to the audience, for many of whom are students. You've spoken with great humility about your career up to your first position at NASA Goddard. What advice would you give to a student today who wants to work at the national or international agency level?
Well, I think the thing that I'm seeing a lot of out of students, we have a lot of opportunities, which is nice at NASA. I think ESA has the same types of summer opportunities. And so folks who really want to kind of work at the agencies, I think particularly at NASA, this I know for sure, the best way to get your foot in the door is to do one of these internships, either in the summer. They also have like a co-op type of internship where you can work during the academic year. You can take time off from your studies and work, or it's really flexible. And pretty much all of our new hires, unless they're already kind of established out in the community, come into NASA that way. And it's a good opportunity for people to see if they like working, doing this kind of work and working in the government, being a civil servant. And I also encourage everybody, today's master's degree is kind of like, your parents' bachelor's degree. To do this type of work now, it's getting so specialized that you really do need a lot of additional formal training. So, if you're considering about going on to grad school, definitely do that. That helps get in. And like I was saying, if you're not an intern, the only types of new hires I've really seen come in really do have PhDs with some kind of either PhD dissertation, very much related to what NASA is doing, or they have some experience, previously. So it's really hard to, as a fresh out kind of bachelor's or even master's, to get selected, because can you imagine when there's an opportunity just for a full-time position, there are hundreds of applications, and so it really helps your chances if you're already a known quantity and you come in and you're a student. Those are still hard to get, but we have a lot more. I mean, even during COVID now, over the past year, we did remote internships, and I think we still had about 200 just at Goddard. So, we have 10 NASA centers and scattered around the country, and they all have an internship program. And when it's non-COVID, I think last year, like in 2019, the last time we did in-person internships, I think we had almost 500 students. So there are opportunities, and that's the best way to get your foot in the door and start to meet the people. And if you do a good job, those people remember you, and they'll keep tabs on you. And and when it's time, when you're done with your studies, you'll kind of be first in line, or at least first for consideration. And at the very least, your name will stand out in that few hundred applications that come through human resources when there is an opening. So that's what I would recommend.
Thank you very much for your advice, and thank you so much for your time and your presentation.
Sure, happy to do it. Hopefully you enjoyed it. And could you hear the sound okay on the videos?
Yeah.
Sounding great on our end. Thank you so much, Dr. Bos. And yes, if you have any final words to say to the audience just before we close out. Thank you.
Well, thanks for your interest. It's always fun to get out and share with the public, especially people who are interested in it, because we love it. Of course, it's sort of my hobby and my job. I mean, I just love everything about space exploration, and it's going to come to folks like you that have that same enthusiasm to carry on and do the next cool things out in space. And even analyzing this data right here, we often talk about how this mission is really built for future generations, because there's going to be better analysis techniques, there's going to be better instrumentation here on the ground 10 or 20 years from now than what we even have right now. And we're reserving a certain amount of material from Bennu just for that opportunity. So it's really folks like you that will probably make the biggest discoveries 10, 20 years down the line. So keep at it, and I think there'll be it's really kind of a renaissance right now in terms of space exploration. You have a lot of commercial companies now that see the value, and there's also money to be made. So I really think this is kind of the second great space race, although it's not between the US and the USSR. Now it's kind of between different companies and who's really going to go out there and be able to put out the infrastructure and make us a spacefaring species. So it's a very exciting time, and glad you're all interested in it.
Fantastic. Dr. Bos, thank you.
Thanks.